Alright, so, welcome back. We're looking at trig substitution, and this is, we're looking a lot at what Paul's Online Notes has to say about this because, I just like the way that they explain it. So, we're looking at a couple examples of when use substitution does work, and then we'll look at when it doesn't work, and then we'll do some more problems. The goal here is to recognize the difference between when we want to use substitution and when we want to try a different strategy. So, here we go. When use substitution does work. So here we have x on the outside of the radical, and then on the inside of the radical we actually get something that's, when we use u equals what's inside the radical, we get 25x squared minus 4. So then du is going to give us, what, 50x dx. And so the x dx works very nicely, where we end up with, what is this? U root u? Du, and then we have a 1 over 50 here. And then we get, what, u to the 3/2 times 2/3 times this 1 over 50, plus c, and then we translate that back into terms of x's, so we get, what is this, like, well, the 2 and the 50 go to 25, so then we have over 75, 25x squared minus 4 to the 3/2 power plus c. So there we go. That's when the use substitution does work. We don't have anything with like division or anything here. So that's really nice. Let's look at another example when use substitution does work, and then we'll start tackling when it doesn't. So here, when we have our u, the same u as what's inside the radical that we had before, the 25x squared minus 4, then du will still give us 50x dx, and so this x dx, that can go into our du, so then we get, this is equal to, what, 1 over 50 du from here, and then 1 over root u. And then that's just the power rule again, where we get, what's that? Well, let's rewrite that as a radical, that radical as a rational exponent, just because I think it's easier to handle. So we get u to the negative 1/2 power, because it was a root u in the denominator, so to make it not in the denominator, we negate. And then we get what? U to the 1/2 divided by 1/2, so 1 over 50 times 2 over 1 u to the 1/2 plus c, and then 25. So we get 25x squared minus 4 to the 1/2 power over 25 plus c, because we have an indefinite integral, so we have a family of functions. Alright, so what happened here that made it possible for the use substitution to work? Well, we have this x hanging out that's just being multiplied by something else. And that x was key for our du to very nicely, very cleanly substitute when we have our u is some quadratic. So what about when we have this? So I'm telling you that the u sub isn't going to work. But can you think about why the u sub won't work? If we have u equals what's inside our radical, then we'll end up with the du is 50x dx, and that isn't going to help us with this x in the denominator. So this is where you're just going to need to trust me. And I'm going to say, let's let x equal 2/5 secant theta, where we're constructing some triangle where the secant, which is hypotenuse over adjacent, is going to give us hypotenuse over adjacent is going to give us like a 5x. There's a theta, and there's a 2. So just trust me on that for a little bit, and we'll see where this gets us. Because we really just want to make our integrand easier to work with. And so let's try this. So if we have x equals 2/5 secant theta, then, well, what can we do with that? If we put that in here, then we get a 25 and then a 2/5 that's being squared and a secant theta that's being squared, and then minus a 4. Okay? And then divided by 2/5 secant theta, and then we have this dx, which is going to give us 2/5 secant theta tangent theta d theta. So then we have 2/5 secant theta tangent theta d theta. Is that particularly helpful? Well, I guess if we look in here, we get this 25 and the 5. Those can cancel out. Let me do that in red. So we got 25 and 5 with the root. So then we end up with, inside our radical, we have 4 secant squared theta minus 4. And we can pull out the 4, so we get a 2 root secant squared theta minus 1. And I think that's actually pretty useful, because if you remember, let's do an aside up here. Remember that sine squared plus cosine squared is 1. So if we divide everything by cosine, that's a bad line, then we end up with tangent squared theta plus 1 equals secant squared theta. And so if we move this 1 over, then we just get, this is a 2 root tangent squared theta. And that's nice, because tangent squared theta and then square root of that is going to give us tangent theta. We got to be a little bit careful, because this is going to be we need to have this as like the absolute value of tangent. So that's important, right? Because that like determines what our output's going to be. It's got to be positive. But other than that, I mean, like, that's pretty good. And where does that get us? Well, we end up with this numerator is going to be 2 tangent theta. And then we have, this is over 2/5 secant theta times 2/5 secant theta tangent theta d theta. And then some stuff can cancel, right? What are we getting? We got 2/5 and 2/5 secant. So we got just tangent squared? Wait, that's really great, because then, yes, I guess we have a 2, right? We have this lingering 2. And then we have integral of tangent squared theta d theta. But remember from up here, tangent theta is secant squared theta minus 1. Tangent is secant squared minus 1. So that's really nice, because we know our integral of secant squared is tangent. Let's write this down. Secant squared theta minus 1 d theta. And so when we integrate this, integral of secant squared, that's tangent. So we got a 2 tangent theta minus theta plus c. Now, that's still in terms of theta, so we're not quite done. And then remember the right triangle that we had drawn up here? I'll draw it again down here. So we have theta, we have a 5x, and we have a 2. So, well, we need tangent, so that's opposite over adjacent. So tangent being opposite over adjacent, we need to figure out what this side is, that opposite side from our theta. And that is going to be Pythagorean theorem-y stuff. So 2 squared plus, let's call it O. That's bad notation. Squared equals 5x squared. So then O is 25x squared minus 4. And that looks, oh, and then square root of that. That looks conspicuously like what we had in our numerator at the very beginning. Remember that? So, that's probably where that secant came from. So then, that gives us tangent theta is going to be root 25x squared minus 4, opposite over adjacent, which is 2, minus, but then what do we do with this theta? What can we do with the theta in order to figure out what it is by itself? Well, we can just take arcsecant, right? Because we know that how we declared x was that it was 2/5 secant theta. So can we just solve for theta? If we have x equals 2/5 secant theta, then that means that 5x over 2 is equal to secant theta, which gives us theta is arcsecant of 5x over 2. So we get arcsecant of 5x over 2, and then plus c. Yeah, there you go. You could make this into a arc cosine of 2 over 5x. That's allowed. You can also clean up the algebra a little bit, but there we go. We got one. It's pretty cool. I wonder how we pulled this x equals 2/5 secant theta out of our brains. Well, we can go through and talk about that. So what about when secant doesn't help? And u sub doesn't help. Because if we're looking at this, okay, so if we make u what's inside our radical, it's not going to work, right? Because this x to the 4th isn't going to, like, get reduced or anything. And then if we say that secant theta, like if we say, let's let x equal something like 3 secant theta, then we're going to end up with, like this, what's inside our integrand, this 9 minus x squared is going to be 9 minus 9 secant squared theta, but then we're going to get that is equal to 9 times negative tangent squared theta, because tangent squared theta plus 1 equals secant squared theta. So in order for the 1 to come before the secant, you gotta negate everything. So that's a bummer. But what if we use something else? What if we used sine of theta instead? And where's that coming from? Well, the pattern will be illuminated a little in the future. So, if we have this 9 minus x squared, let's suppose that 3 sine theta is equal to x. So that means that in our radical we get 9 minus, inside our radical we have 9 minus x squared, which is going to be 9 minus 9 sine squared theta. So that's going to give us 9 times cosine squared theta. And that's nice, because then we end up with, in our integrand, and then dx is going to be 3 cosine theta d theta. So then we have 1 over 3 sine theta to the 4th power from there times root 9 cosine squared theta, and then dx is 3 cosine theta d theta. And now, let's see what happens. Well, actually this and that go away, because those are the same, so then we end up with just integral of, was that 81 sine to the 4th theta d theta? And then, like, does that help us at all? Well, I mean, that's cosecant, right? So we get 1 over 81 integral cosecant to the 4th d theta. And then can we deal with that maybe, like, if we factor that a little bit? So if we have, so cosecant to the 4th is going to be cosecant squared times cosecant squared, right? And then cosecant is, let's see, so we have sine squared plus cosine squared is 1. So then if we're dividing by sine, then we get cosecant is 1 plus cotangent squared theta times cosecant squared theta. And so in our integrand, this is actually what we have. Now I wonder if that's going to be helpful. Well, I guess we could do U substitution, right? Because the derivative of cotangent is negative cosecant. So then how does that help us? Well, if we have, and let's change to this one. If we have this is equal to 1 over 81 times the integral of 1 plus cotangent squared theta cosecant squared theta d theta, and then we let u equal cotangent theta. Then du is going to be negative cosecant squared theta d theta, which is there, kind of, I mean, negate everything, and then we'll still be okay. So then we get, what is this? Negative 1 over 81 times 1 plus u squared du. And that's delightfully simple, that we get this is negative 1 over 81 times u plus u cubed over 3 plus c. And then u, we can get our cotangent back. So then going back to here, we get, let's go sideways. So we get, negative 1 over 180 u, which is cotangent theta, plus cotangent cubed theta over 3 plus c. And then we can draw our right triangle. And then we said theta, sine of theta, 3 sine of theta was x, which means that sine of theta is x over 3. So that means that x over 3 goes there, and that means that over here we have root 9 minus x squared because of Pythagorean theorem. So then our cotangent we can translate into terms of x. So our cotangent theta is going to be adjacent over opposite, so that's root 9 minus x squared over x. So we have this equal to negative 1 over 81 times root 9 minus x squared over x plus root 9 minus x squared over x to the third We got a 1/3 there, and then a plus c. And there you go. So the question you might be asking yourself now is, where on earth did this triangle come from so that we could get this? And actually, I would say that this is where you should start. You should start with drawing a right triangle, trying to make sense of what you have in your integrand so that you can use a substitution that makes sense. So we're going to look at some stuff. So in general, if you have your x squared before you have something that you're subtracting from it, then you need to think, okay, this seems like a secant thing. And similarly, if you have subtraction, but you have your constant term before you have your x squareds, then you need to think, okay, this looks like it's going to be some sort of sine thing. And then if you have addition, then you're going to need to think, okay, so this is going to be a tangent thing. And the general way that I strongly recommend that you do this is just by drawing a triangle and saying, okay, when is this side going to happen in my triangle? And the way that this is going to happen is when you have your variable expression as your hypotenuse and your constant term as side. And then here your constant term is going to be your hypotenuse, and your variable term is going to be your side. And here, your hypotenuse is going to be like the unknown side. So that's the general idea, where we have the trig substitutions that we're going to do are going to be either a secant, a sine, or a tangent. And it is important to keep in mind what your theta is allowed to be, because if you break the trig function, then your function your substitution no longer works. So these are the patterns that you should look for, and draw a triangle. So what happens if you don't get one of those forms? What if what you're given looks not like something squared minus something else squared, or something squared plus something squared, sum of squares or differences of squares inside your radical? Well, you should probably use completing the squares so that you can get what you want. So completing the square, if you recall, is where you have like something plus ax squared plus bx plus c, where you want to like effectively like massage this into a form where you have something squared with this x and this like k and then an h. It's like effectively pushing it into vertex form. So for x squared minus 4x, what do we need to do so that we get a perfect square trinomial, and then we take away what's not necessary? So like x squared minus 4x plus what minus what will give us 0, so that we get like a x. I think we should probably aim for a minus 2. So negative 4 divided by 2 is 2, and then square that, it's 4. So that'll give us this part. But since we added 4, we need to subtract 4. And that's lovely, because then we have x minus 2 squared minus 2 squared. And this whole thing, well, that's going to be our, we have our x term in the beginning, and then we have a difference, so that means that we're looking at a secant. And so let's try to tackle that. Let's look at this. Some space. So we have a secant theta, and that's going to be wait, hang on. Sorry, I had to pause and think. Okay, so we have this as our triangle, where we have theta and we have our x minus 2 as that side, our 2 as this side down here from our secant pattern, where secant theta is x minus 2 over 2. So that gives us this unknown side is x minus 2 squared minus 2 squared, which is 4. And that is what's over here. Okay. If we move things around, then we get 2 secant theta is going to be x minus 2, so if we add 2 over here, then that's okay. And then let's differentiate. So we get 2 secant theta tangent theta d theta equals dx. And, well, this tangent theta is going to be root x minus 2 squared minus 4 all over 2. So then our denominator up here is going to be 2 tangents, right? So then we get integral with dx, we have 2 secant theta tangent theta d theta, 2 secant theta tangent theta d theta over, and then we got 2 tangents here from this. So we got 2's to cancel, pew pew, tangents to cancel, pew pew, and we're just left with integral of secant theta d theta. And this, I mean, it looks simple, but it's like, it's not. Because we know secant squared, but do we know secant? Like, is secant the derivative for anything? Well, I think we need to do a little bit of thinking. So, let's see. What color should we think in? Let's think in this like teal thing, seafoam. So let's think. If we have secant, remember that we had log integrals, where we were effectively looking for like something, the natural log of u to be u prime over u. That was like a thing that we would think through when we have our derivative over our input. So can we like get this secant kind of into that form where we have secant of theta to be this u prime over u format? So I think so. What u would we need to use? Well, if we said that u was secant of theta plus tangent of theta, then du is going to be secant theta tangent theta plus secant squared theta, and then d theta. And so what would that be? Secant theta tangent theta plus secant squared theta d theta over secant theta plus tangent theta. So, are we getting the format that we want? Well, I think we are, where we're getting that the natural log of secant theta plus tangent theta plus c is going to be our integral of secant theta d theta. Natural logs. So, then we get, let's see. So, just to clarify, if we're looking at the derivative here, if we're looking at the derivative of secant theta plus tangent theta, then we get this. So that means that, let's do this in. So that means that du is going to be secant theta times tangent theta plus secant theta with our d theta tagging along. So that means that secant theta, that means that if we divide both sides by tangent theta plus secant theta, that means that we're dividing by u, so then we have du over u is secant theta. So that's where this came from. And that's our log form that we wanted. So going back up here, this secant theta is going to be natural log of secant theta plus tangent theta plus c. And then we need to translate that back into terms of our x's, because that's what our original integrand was in terms of. So that's, oh my gosh, where is that? Tangent. So natural log of secant, which is x minus 2 over 2, plus tangent, which is root x squared minus 4x over 2, plus c. Oof. Cool. So that is trig substitution, and always remember to translate it back into terms of what you are dealing with in the beginning. And yeah, that's about it.